we have Cristhian Garay speaking about a specialization of divisors of real, metrized complexes of curves.
Thank you. First of all, I'm very grateful to be able to speak here in this wonderful conference. And the talk is going to be divided in two parts. The first part, I discussed this technique that we have decided to call specialization via tropicalization. And in the second part, I will try to give an application of these ideas to a concrete problem in real enumerative algebraic geometry. So these are the parts. First, I will talk about some preliminaries. Then I will talk about some relationship between tropicalization and skeletal Berkovich spaces. Then the definition of this process and some remarks about the real part of this story. And in the second part, I will introduce the problem in which I am interested in, and the second part are the results. So to start with the first part, specialization via tropicalization. Roughly speaking, a real metrized complex of algebraic curves can be seen as a tropical curve with algebraic models, and this object coming from a real Berkovich curve. So a model, for me, it's going to be an algebraic curve, proper and smooth, over the residue field. Specialization, well, this process has several names in the literature, but specialization for me refers to a method to transfer divisors from an algebraic curve over a non-Archimedean field to one of these combinatorial objects which is associated to this curve. The bridge that allows me to go from one side to the other side are analytification process, which is found in the Berkovich theory. And in this first part, I will describe the main ideas to define this thing using what I call embedded tropicalization. So to start with the preliminaries, during all the talk, I will focus on this field. So I will call it K. But in the literature, there is also this notation, and it is just the set of all formal series, power series with variable t, with coefficients in the complex numbers, and index of support varying in a well-ordered subset of Q. This field has many good properties. For example, some of algebraic properties that this field is algebraically closed of characteristic 0. Some analytic properties is that this is non-Archimedean complete or Banach with respect to this theoretic norm, which is the only norm that I am going to use on this field. It is also spherically complete. This is a technical requirement to avoid points of type 4 in the analytification, and also has good real properties. Remember that a field is formally real if -1 is not a sum of squares. So we have that this field can be seen as the algebraic closure of a real field. In this field, -1 is not a sum of squares, so it's formally real, and its residue field is also real. So I'd like to think about this field with the non-Archimedean valuation here as a non-Archimedean version of the complex numbers with the usual valuation.
I'm sorry, I'm confused. On which sense -1 is not a square for this field K? Is it C?
Yeah, this because you need to introduce a square root of -1, and if you restrict your elements here just to real numbers here.
But your definition of K is complex number, right?
Yes, but I am defining here a subset, a subfield. Yes. So this subfield just consists of real numbers here. So yeah, I'd like to think about this field as a non-Archimedean version of this complex field with the usual norm. So my conventions is that a real curve is a smooth proper geometrical integral scheme of dimension 1 over either one of these fields, either KR or R, or a pair consisting of a curve over K or C together with an anti-holomorphic involution on the rational points of the curve. The real part is the fixed part. I will continue with the analogies between these two fields. For example, this usual isomorphism of sets sending a number to the logarithm of the absolute value and the argument gives us the traditional amoeba-coamoeba pair. And in the case of K, we have another decomposition, and the first projection gives us the non-Archimedean amoeba, and the second one gives us what is called an initial coefficient. I will show you that these two maps are very related to each other. In fact, it would be also interesting to study the third projection onto the valuation ring. So I will take a polynomial, Laurent polynomial, infinitely many variables, and I will consider the hypersurface inside the torus. So since the evaluation group is Q, I can take Euclidean closure, and that's the tropicalization of the hypersurface. That's why we frequently write that the composition is the tropicalization, even if it is not completely correct. So recall that a point in the tropicalization belongs to the tropicalization if and only if the initial degeneration, which is a polynomial in the residue field, has zeros in the torus. And this is an innocent remark that allows us to define all the process. If I have a point in the hypersurface, non-Archimedean hypersurface, such that its tropicalization is a point P, remember that P is in Rn, then the initial coefficient of this series, of this tuple of series, belongs to the variety induced by the initial degeneration of the point. In other words, for any point in the tropicalization, there is a specialization or reduction map that comes from the preimage of the tropicalization over that point to the variety in the residue field defined by the initial degeneration of the same point. So this is the general setting. From now on, I will restrict to the case of two variables to talk about curves. So I will take a smooth proper toric surface, and I will say that hypersurface compactified in this toric surface is Berkovich adapted if the first thing is smooth, because I don't want to deal with open subscheme, with open schemes or singular schemes, so I just assume that X is compact or proper and smooth. And I will ask for two more conditions. Every finite length edge in the tropicalization has weight 1, so I can allow infinite edges of weight greater than 1, and each model, each curve in the toric in the torus is smooth for every vertex of my tropical curve. And I will call, if all these three conditions are satisfied, I will call that trop X is inside the tropicalization of the toric surface, is an embedded tropicalization. So I will take this pair, a curve inside a toric surface, which is Berkovich adapted, and I will take its Berkovich analytification. This is a Berkovich space associated naturally to the curve. So the theorem is that there exists a marked skeleton for the analytification and a continuous map, this map surjective, of this analytic object, this skeleton associated to the analytic object, to this combinatorial object, which is a tropicalization. And this map is continuous and also is M to 1 over an edge E of the tropicalization of weight M. In particular, since I am asking that every finite length edge of the tropicalization has weight 1, I am saying that, well, let me continue. And I call this marked skeleton because there are some points of type 1 which are associated to this skeleton, which are precisely the intersection of the rational points of my curve with the toric boundary. And all these points are of type 1. The model over any vertex of this skeleton is the unique smooth projective complex curve having this as field of rational functions. So what is important here is that when I have this situation of Berkovich adapted curve, the marked skeleton, which is usually a hard object to describe, even combinatorially, and the models, it is hard to say which one are them, is almost the embedded tropical plane curve, which is trivial because we know that it is just a subdivision. But moreover, I am telling you here which are the models over each one of the type 2 vertices of the skeleton. And yeah, this is what I'm telling here. So I am going to use this theorem to define the specialization process. So I am going to take the retraction restricted to the rational points of my variety to the skeleton, and I take a divisor here. So note that the boundary points or the mark points of the skeleton are fixed by the retraction. The retraction just takes all the rational points and then it let this retraction to evolve to the skeleton, and the specialization in this sense is to see where the point lands on this finite curve. And I'm saying here that these points are fixed by this function. So this divisor, which I will call specialization, is just let evolve the contraction of the whole space onto the skeleton. And then here I use the specialization map that I introduced before, and this gives me what is called a divisor on a metrized complex of curves. So it consists of two parts. It consists of a divisor on the tropical curve, and it consists of a divisor of the corresponding degree over any of the models. So this process has a real part. Suppose now that the polynomial is defined over this subfield, and like before, this curve is Berkovich adapted. So all these objects are the objects that we have defined so far are real. The rational points of k of x is a real algebraic curve, but now real over in this sense that it has an anti-holomorphic involution. Also, the Berkovich skeleton, the analytification is a real Berkovich curve in the sense that it also has an anti-holomorphic involution at the level of Berkovich spaces, which restricts to this anti-holomorphic involution that I had at the level of algebraic spaces, algebraic curves. But each of the models also is real because this is just the initial degeneration of a polynomial at a point. And since this polynomial is real, this initial degeneration is real. So the polynomial descends to R. So all the models have a real structure also. And the specialization map sends real divisors to real divisors. So this construction will allow me to do some real algebraic geometry. So to conclude this first part, given a Berkovich adapted curve inside a toric surface, I defined this map. So the pros of this map is that this gives an alternative standard. This gives an alternative to the standard approach to use semi-stable models over the evaluation ring for X. Also, implicitly this method selects one such model for us. So before this technique was introduced, if you wanted to do something like that, you needed to select a semi-stable model for your curve and then go to the special fiber and then a lot of algebra. And you lost control over the models, you lost control over almost everything.
When you say you need it for which purpose?
Sorry?
When you say that you need it for which purpose? Which purpose?
This thing, I will discuss an application in the second part. So yeah, the second pros is that I can compute concretely the models associated to the type 2 vertices of the skeleton. This is well adapted for application to real geometry, I believe. This is work in progress, and this has some sort of regeneration theorem for limit linear series on the skeleton. I will talk about this in the next part. The cons are somehow that this is very limited because so far this seems to work for hypersurfaces that are defined hypersurfaces of toric varieties. And in this case, I am just talking about curves. Meanwhile, the method that uses semi-stable models works for all the cases. So I will now talk about an application. I will show you how the previous ideas may be applied to a solution to a concrete problem in real enumerative geometry. This is joint work with Indranil Biswas from Tata and Ethan Cotterill from Brazil. So, in fact, I am telling you the story the other way around. I am telling you some sort of generalization of something that came out analyzing this problem and now has become a body in itself, but in fact this was the problem that inspired us to do the previous things. So I will take a real hyperelliptic algebraic curve over the true reals with non-empty real part of genus greater or equal than 1. So I have a 2-to-1 map to the complex sphere, and I will denote by D its class in the Picard group. I will take this real line bundle of degree 2k for k at least the genus plus 1. And I will take the whole real vector space of sections of this line bundle over C, and this is its dimension. So the question that motivated everything, all this, is what can we say about the distribution on the real part, which is non-empty, otherwise the problem would be trivial, of the real inflection points of this G2k to k minus G, defined by this line bundle and this real vector space. In this case, this number varies between 0 and the complex number, which is independent, which just depends of G, the degree and the rank, which is this one. So to use the previous ideas, I will start by constructing a Berkovich adapted hyperelliptic curve inside this toric surface, and I will just discuss about the genus 3 case to keep things at an easy level, and I will use Viro's patchworking technique to do this. So I will, to do Viro patchworking, I just need to select a convex polygon. In this case, I will, for some reasons of symmetry, I decided to ramify my hyperelliptic curve at 0 at infinity, so this is why I'm not taking the whole triangle, just this one. And I take this particular subdivision so that each triangle has a unique integer point to get the generation of a hyperelliptic curve into a chain of elliptic curves. So I just need to take this lifting function, so that the values that I put here induces this triangulation as the projection of the convex hull, of the lower convex hull. And with this function, I define this polynomial, which is defined over the real numbers. So I just take some real numbers different from 0 every time the value here is not infinity. I put t and I raise it to the power of vi, which is this number, and put x here and y. So this is my affine model, and I will compactify this thing inside a toric surface, and I will work with this object. So this is my polynomial, and this is a real curves. In all the numbers here are real. So I will take the toric surface kp1 cross kp1, and I let x be the compactification inside here. Right. So this is now a non-Archimedean curve, proper and smooth. Well, I say here when the resulting object is proper and smooth, it's always proper but smooth, if and only if the polynomial is separable in x as a non-Archimedean polynomial. So the only thing that I need to ensure that this object is Berkovich adapted is to ask that the models, that's to say the polynomial restricted to each one of these triangles, which is an elliptic curve, to be smooth. So if this is the case, then all these things give me a Berkovich adapted curve, and I can work out this computation. So here, this is the drawing for G. Just think about G equal 3. So there is a real G2k minus 3 defined on this hyperelliptic curve over the non-Archimedean field, this one. There is a way to specialize this to a crude limit in the sense of Omida, Amini, and Amini-Baker, which work with this kind of object over complexes of metrized complexes of curves. This is a metrized complex of curve. So it consists of a tropical curve the length of each one of the red edges is finite, and the length of each one of the black edges is infinite. These, all the points that are black here correspond to points of type 1 in the Berkovich analytification and are the marked points. The red part is like the non-marked skeleton associated to this curve. So this, and over each one of the red vertices, I have a complex elliptic curve. Which one? This one. I just have to restrict my whole polynomial to the triangle, and since I assume that this is smooth, I can carry away the process of specialization to get a real divisor here. So the specialization, I am talking about linear series. I have to tell you which one is the specialization at the level of rational functions. The specialization at the level of rational function is also given by taking the initial coefficient of each one of the functions. So what we have done here is to specialize a complete real linear series on the non-Archimedean hyperelliptic curve of genus 3 into 3 linear series which are now non-complete over 3 different elliptic curves. So I have a whole linear series, complete linear series over a non-Archimedean curve, and I have here 3 elliptic curves. And what this process does is that your whole linear series specializes to one linear series over each one of these elliptic curves. Now the problem is that these series are no longer complete. They have a codimension 2 subseries of this complete linear series now seen over each elliptic curve, which are the models. So this gives an alternative to the method developed by Amini and Baker for the theory of limit linear series on metrized complexes of curves, and the advantage is that we have control over the models. But there's more. In this case, we have a regeneration process given by the Johnson-Vito method, which allows to solve the initial problem for real inflection points using unreal hyperelliptic curve locally over each elliptic component, and then patch all the solutions to get a global solution. So this is the tropical philosophy. You want to solve a global problem, you just localize it, you solve it locally, and then you try to go back. So in this case, this is possible. And let me just finish by describing you this Johnson theorem and the Johnson-Vito method, which I will just see this as a surface compactified inside CP1 cross C. So it is not proper. So it's a surface because it has codimension 1 here, and this inclusion of rings gives me a surjective morphism over the torus. So what is important about this is that associated to this morphism there is a topological space together with a continuous map over this space. This space is the classical closed disk of radius E-1, the complex disk. And this map is obtained using the theory of hybrid Berkovich spaces. So I will not discuss it. But the properties are very interesting because each fiber if you take a point here, a closed point over a point over the disk which is not 0, moreover it is restricted to a real positive number, then the fiber of this map is just the usual or holomorphic analytification. In other words, for each real point in the positive part, I am getting a real hyperelliptic curve. So this is just I just have to plug A instead of T. But the interesting part is that the fiber over 0 is the non-Archimedean curve that I had. So this gives some sort of continuous deformation from holomorphic fibers to non-Archimedean fibers. And what is important is that for small radiuses already of the disk, the map P is continuous. So this is the process that allows us to deform the tropical solution to a classical solution by using continuity of this map. I think that's what I said. Thank you.
the answer to the problem of distribution of?
Yeah. So far we just were able to give an answer about the ramification points of the hyperelliptic part, because on each elliptic curve we have a non-complete series. So we need to work more to know how many real points can we do. But so far I can tell you that all the ramification points which are real stay with the same multiplicity as real inflection points of the hyperelliptic curve.
Any other questions? Well, Cristhian, thank you very much.
Thank you.
And we have the sunset seminar in 20 minutes, you know where. We'll be there.